Good afternoon, my name is V. Pradeep Reddy and I am from Aeronautical A section. My analysis of aircraft structures topic is turbulent dynamo action in a shear flow. Abstract. We perform numerical experiments to study the shear dynamo problem, where we look for the growth of large-scale magnetic field due to non-helical steering at small scales in a background linear shear flow. In previously unexplored parameters regimes, we demonstrate the large-scale dynamo action in the limit when the fluid Reynolds number is below unity, whereas the magnetic Reynolds number is above unity. The exponential growth rate scales linearly with shear, which is consistent with earlier numerical works. The limit of low Reynolds number is particularly interesting, as seeing the dynamo action in this limit would provide enough motivation for further theoretical investigations. Introduction. Magnetic fields observed in various astrophysical systems such as the Earth, the Sun, the disk galaxies, accretion disks, etc. possesses large-scale magnetic fields in addition to fluctuating component. The magnetic field survives for time scales much larger than the diffusion time scales in those systems and therefore are thought to be self-sustained by turbulent dynamo action. The standard model of such a turbulent dynamo to produce large-scale magnetic fields involves amplification of seed magnetic fields due to usual alpha effect. The model and numerical setup. Let E1, E2, E3 be the unit basis vectors of a Cartesian coordinate system in the laboratory frame. Using notation x equals to x1, x2, x3 for the position vector and t for the time, we write the total fluid velocity as s x1 e2 plus v, where s is the rate of shear parameter and v of x comma t is the velocity deviation from the background shear flow. Mean field induction equation. Case of incompressible magnetohydrodynamics in background linear shear flow with a non-helical random forcing at small scales. In order to do that with pencil code, we limit ourselves to the cases for which the root mean squared velocity VRMS is small compared with the sound speed, making the Mach number is very small. Formula for dynamo action. Results and discussion. Numerical studies of dynamo action in a turbulent shear flow. Summary of simulations in different parameter regimes. A1 RE equals to 0.47, RM equals to 0.47, KF by K equals to 10.03, minus SH equals to 1.27, MA equals to 0.0235, grid 64 power 3, no dynamo. A2 0.73 Reynolds number, 0.91 RM, KF by K equals to 10.03, minus SH equals to 0.41, MA equals to 0.0727, grid 128 power 3, no dynamo. A3 RE equals to 0.76, RM equals to 0.57, KF by K equals to 1.54, minus SH equals to 2.78, MA equals to 0.0701, grid 128 power 3, no dynamo. B1 RE equals to 41.20, RM equals to 0.82, K by K equals to 3.13, minus SH equals to 0.186, MA equals to 0.258, 64 power 3, no dynamo. B2 RE equals to 4.65, RM equals to 0.69, KF by K equals to 10.03, minus SH equals to 0.0285, MA equals to 0.139, grid 64 power 3, no dynamo. B3 4.99 RE, RM equals to 0.75, KF by K equals to 10.03, minus SH equals to 0.133, 0.150, MA, grid 64 power 3, no dynamo. C1 0.59 RE, RM equals to 29.47, KF by K equals to 5.09, minus SH equals to 0.12, MA equals to 0.03, grid 128 power 3, no dynamo. C2 0.59 RE, RM equals to 29.47, KF by K equals to 5.09, minus SH equals to 0.66, MA equals to 0.03, grid 128 power 3, dynamo. C3 RE equals to 0.85, RM equals to 25.50, KF by K equals to 5.09, minus SH equals to 0.226, MA equals to 0.129, grid 128 power 3, dynamo. C4 0.75 RE, RM equals to 33.060, KF by K equals to 10.03, minus SH equals to 0.236, MA equals to 0.0674, grid 128 power 3, dynamo. D1 RE equals to 1.04, RM equals to 41.66, KF by K equals to 3.13, minus SH equals to 0.367, MA equals to 0.13, grid 128 power 3, dynamo. D2 RE equals to 1.79, RM equals to 89.57, KF by K equals to 5.09, minus SH equals to 0.215, MA equals to 0.0911, grid 128 power 3, dynamo. Thank you.